In our last video, we talked about confidence intervals. In this one, we're talking about confidence intervals again, only now we're going to be selecting the sample size. We're going to be using the same example from the last video. The tacks being thrown, landing point up. This is just copied right out of the last video, and you can see we have our confidence interval, 98% confidence interval, right down here. Now, we're going to introduce a new term, this margin of error, right, which is going to be half of the width. Right, if you think about it, if we split that down there, this is our margin of error, right, half the width, which in this case is 17.2%. We can actually write this confidence interval in a form that uses that margin of error that looks like this. So we could say that the confidence interval is 28.9% plus or minus 17.2%, which 17.2% in comparison to about 29% is a huge margin of error. It actually makes this confidence interval maybe not so useful. We have high confidence, but we have a really big margin of error. So the question is, how do we reduce that margin of error? Well, that's all based on the spread. So to reduce the margin of error, we have to change the sample size, that 38. So what does changing the sample size do? If we look at a population distribution and we take a sample size 7, for example, we get a sampling distribution. And that sampling distribution, if we look at a 98% confidence interval, will have a certain margin of error, like what we calculated before. If we then take a sample of 20, what happens to the sampling distribution? It gets smaller, it gets or more narrow, right? Because sample size, this n, is in the denominator of the spread. So if you increase n, the spread decreases. And you'll get a margin of error for a same 98% confidence interval, which is smaller than if you took a sample size of 7. So you can see that increasing sample size effectively reduces the margin of error for the same confidence interval. Well, that's exactly what we need. What we need to do now is reverse the process. Right? Here we're going to use our tack example. We have the results of what we did before, our 38 throws of the tack. What we can do is say, for a new question, what is a sample size that would give a 1% margin of error for a 98% confidence interval? Right, so we're going to need the z-score method, which, if we use the inverse norm, if you're used to using the inverse norm, you're going to have to use the z-score method for this calculating the sample size. Notice that this margin of error is exactly the same as this term, z times standard error. Well, we're going to use that as an equation, which will look something like this. Our margin of error, or our z times standard error, has to be less than or equal to the margin of error that we are looking for. So what we're going to need, we have this margin of error, that's this 1%. Right? We need this z-score, which we can get, we put in the 1%. And now we get our z-score by looking it up in the z-score table using our standard method, our area to the left. And then we can plug in our numbers, our p-value and our z-score. We can calculate it, and we get that the sample size, the number of times we'd have to throw this tack, would have to be over 11,000 times in order to reduce the margin of error to only 1%. Remember, it was 17% before. So it would take quite a number of trials or a big sample size. Let's look at, of course, we'd have to verify by using the z-score or inverse norm. Right? We have to verify that using normal is a justified distribution to use, which it is. And now I want to draw your attention to the fact that in our calculation here, right, this 0.89289, that came from this 38 tosses that we did initially. This is called a pilot study, right? That gave us an initial value so that we could work with it in this equation. Well, we don't always have a pilot study, which is what example 2 is going to be like. 2 candidates are running for public office. A polling company wants to conduct a survey to see within a 3% margin of error, what percentage would vote for candidate A if the election was today. They want to be 96% confident. How many people should they poll, right? That's a sample size question. We're going to use our same margin of error equation or inequality. But notice we don't have a value for p this time. We could get z, right? But p, we have to essentially guess at that. And because we're guessing, what we want is the most conservative estimate possible. Now, when we're talking about proportions, that's kind of convenient because p-values range from 0 to 1, and that's it. So if we look at a good spread of proportions and we multiply by 1 minus p, we can see that the biggest value is 0.25. If we make the numerator the biggest value, that's going to force the n to be also the biggest value possible. So we're going to use 0.5 as our most conservative estimate. And that's what you always do. We can get our z-score using the z-score table, or we could use the inverse norm to also get the same z-score. We then plug in our values. Notice there's 0.5 in for p. Our z-score is in there, 0.03 for our margin of error, and we get that we should poll 1,168 people at least. A detail here that's important. Notice that in the calculations we got 1,167.36. If we were to round to the nearest whole number, it should be 0.7 or 67 rather. Well, because of the inequality, we always have to go up, or it will actually be slightly less, or slightly more rather, than the 3%, and we don't want that. We want a 3% or less. So you always actually have to go up from your original calculations over here. Now we do need to verify that using inverse norm or the z-score table is justified, and it is. Oops. And I need to plug in. Hold on. Moving on to example 3, we're going to start talking about means instead of proportions. Whenever the professional football team plays in the local stadium, literally tons of trash is produced. Over the last 35 games, the average amount of trash produced was 4.65 tons each game. Trash data has been collected over many years, and it is known that the standard deviation is 0.94 tons. How many games, right, that's asking for n, would you need to average in order to have a 95% confidence interval with a margin of error of 0.25 tons? Notice the units on the margin of error is the same as the mean. That's true for proportions as well. Proportions are percentage, which is why we are looking for a margin of error of 3%, for example. But in this case, because we're doing averages or means, right, the units of the margin of error in this case is tons. So we have our same margin of error. That should be an inequality. Sorry about that. There we go. We have z times our standard error. Right, we can get our z-score. Right, we're assuming that the normal distribution will be verified. We can do that once we get our n value. And then, well, here it is. We have our n, or our verification. And then we, of course, plug in to our equation. And it turns out that we would need to average at least 55 games. Again, notice that from 54.3 always went up to 55 in order to get the margin of error we're interested in. Now in this case, z-score and normal distribution verified. What happens if that is not the case? Right here, example 4, the ages of 12 randomly selected billiard tables around the city are found. The average age of the 12 tables is 8.3 years with a sample standard deviation of 3.6 years. All right. How many billiard tables, again that's n, would you need to randomly select in order to determine 95% confidence interval with a margin of error of 1.5 years? So it verifies to be a t-distribution. Well, we're going to do the exact same thing, only using a t-distribution. Right, here's our margin of error using t instead of z. We get our t from the t-table. Degree of freedom in this case is 11. Right? Notice that different than a proportions question, right? We actually have to have a pilot study. Right? We have these 12 randomly selected tables as a beginning point. Right? We actually could, with proportions, estimate being conservative without a pilot study, but that's actually not possible with means. We actually have to have some kind of pilot study to begin with. And of course, we calculate, and in this case, we would need to randomly select at least 28 billiard tables around the city in order to get the margin of error that we're interested in.